Hey everyone, Mr. Fransky here. We're just going to go over the big idea of the fundamental theorem of algebra today. We talked about this in class, but we're still struggling with it a little bit. So we want to take a look at just kind of what the idea is behind the fundamental theorem and how we can factor every polynomial. So let's take a look at what we're talking about here. The whole idea of the fundamental theorem of algebra is that every single polynomial can be factored. So no matter what my polynomial is, grab a color here, no matter what polynomial I have, p of x, this is saying that we're able to factor that into all of its factors. So x minus some c1, I don't know what it is, and then there'll be x minus c2, x minus c3, and this will keep going for as many factors as the number that I have for the degree of p of x. So it'll be x minus cn. So this would be if the degree of p is n. So if I have an nth degree polynomial, I will have n zeros. That's what we were able to prove from the fundamental theorem of algebra. And then with all of those n zeros, I'm going to be able to make these n factors. Now, some of these might be repeated. We talked about multiplicities the other day. So some of these are going to be, it's possible it could be repeated. So we could have x minus 2, x minus 2, x minus 2. But the point is, if we count all those multiplicities, we'll have a total of n zeros. So in here, we have n factors, and those represent the n zeros. So if we listed them out, if we listed the zeros out here, it would be c1, c2, c3, all of these numbers. Each one of these is a 0. If I plug it into the polynomial, I'll get 0. And so each one of these is a factor by just subtracting those. Because if I plug in c1, those will cancel. Plug in c2, those will cancel. And I'll end up with 0 for the whole thing. So if I have degree n, the important thing here is that I have n factors and n zeros. That's what the fundamental theorem of algebra says. So, for example, I could have this polynomial. It's a big polynomial. Our degree here is 6. So n is equal to 6. So how many factors should I have? Well, I should have 6 factors. So I should be able to set this equal to x minus our first 0 times x minus our second 0 times x minus our third 0 times x minus our fourth 0 times x minus our fifth 0 times x minus our sixth 0. Now, I don't know what these zeros are. The whole point of this is that we want to be able to find what those zeros are, and then we'll be able to have this factorization of the polynomial. So the question is, how the heck do I get those? Well, if they're real zeros, we can get them by graphing. So graphing would be a great way to do it. Graphing is one way we can do it. Sometimes they'll give us information, so we could be given the zeros. So if they tell us, 3 and 2 are zeros, then we can plug them in here. It'd be x minus 3, x minus 2. And in this case, the reason I chose this particular polynomial, is because when we graph it, it gives us some really nice numbers. So let's take a look at the graph of this. So I graphed this on my Inspire. You can graph it on any graphing calculator. And I graphed our exact same polynomial, x to the 6th plus 3x to the 5th minus 41x to the 4th minus 87x cubed plus 400x squared plus 444x minus 720. That's exactly the polynomial I have graphed here. Now, we know that the zeros of this polynomial are going to happen wherever it crosses the x-axis. So it looks like we have 1, 2, 3, 4, 5, and 6. Hey, great. So all of our zeros are real because degree 6 polynomial, we should have 6 zeros, including complex and real. And here we have it crossing the axis 6 times. So all of my zeros are real. Let's see where the zeros are. Negative 1, 2, negative 2, 3, 4, 5, 6. Let's start at the bottom. So we have a negative 6 is a 0, negative 5, negative 4 is a 0. Negative 2 is a 0. That's supposed to be 4. And positive 1 is a 0. 2, 3 is a 0. And 5 is a 0. So here we have 1, 2, 3, 4, 5. We have our 6 zeros. So if those are our zeros, then our factors, this comes from factor theorem. Everything's kind of coming together in this section, 7.6. So our factors here are going to be x plus 6. Because really that's x minus negative 6, right? Because we're subtracting all of our zeros, we just change that to x plus 6. And if I plug in negative 6, they'll cancel out to 0. So we'll have x plus 4. We'll have x plus 2. x minus 1, x minus 3, and x minus 5. So these are all our factors. So actually, the factorization of this degree 6 polynomial is, this is the same as writing out x plus 6 times x plus 4 times x plus 2 times x minus 1 times x minus 3 times x minus 5. So if I multiplied all these factors together, if I expanded this out, it would take a lot of boxes, right? You'd have to make a whole bunch of boxes to be able to multiply these all together. We would end up with this exact polynomial. So this is kind of the simplest way to be able to factor a polynomial, is if we can look at the graph. We can look at the graph like we have here, and we see that they are all real zeros. If they're all real zeros, they all actually cross the x-axis at those points, then we can just label out all of our factors, and we're done. We have been able to factor a 6th degree polynomial with its 6 factors. But unfortunately, life is not always that sweet. Sometimes we might not be able to graph it. So one situation, we might not be able to graph it. Maybe it's only a baby calculator test or something, so we can't graph it on our calculators. Another option is that it's possible we have complex zeros. So if you graph, like, I don't know, maybe a quartic equation. Let's do it up here quick. Maybe you graph a quartic equation and it looks like this. Well, what's the issue with that? It never crosses the x-axis, so I can't find any zeros even by graphing it. So they might give you a polynomial like this. We're talking about a 4th degree polynomial, so maybe they give you a 4th degree polynomial here. And right now, all we know is that this is going to be factorable into 4 factors. Because that's what fundamental theorem of algebra allowed us to prove, is that if we have a 4th degree polynomial, it's going to be x minus the first factor, c1, x minus the second factor, c2, x minus the third zero, c3, and x minus the 4th factor, c4. Gotta be careful what I'm calling zeros and what I'm calling factors. So our 4 factors here, we should be able to factor this polynomial into 4 factors. Some of these might be complex, some of them might be real. Right now, at this point, we have no idea. We don't know what they're going to be. So this is kind of similar to if we were given a number. So think about the number like 210. So we're given a number. That's kind of like our polynomial. So if I told you there are 4 factors that go into 210, so 4 numbers that multiply by each other to get to 210, well, we could find them because we know there are ways that we can plug in numbers and try to multiply them to get to 210. And it turns out that 210 is 2 times 3 times 5 times 7. So we can find them with a number, but we can't find them with a polynomial. But it's surprising how similar it is to use the numbers as factors as if we were using these linear x factors up here for the factors of our polynomial. It's actually not that different. So how can we find these? Well, the problem would have to give us some hints. It would have to give us some hints. So we're going to be using this as we go on here. That's why I decided to pick this number 210. So it would have to give us some kind of a hint, like maybe it tells us a couple of the zeros. So they're going to give us some sort of a hint here. And in this case, they tell us that 3 and negative 1 are zeros of p of x. So they tell us 3 and negative 1 are zeros of p of x. Well, what that means is if I plugged 3 in here, it would end up giving me 0. If I plugged negative 1 in here, it would end up giving me 0. So factor theorem tells me I now know 2 of my factors. One of my factors is x minus 3. Another factor is x plus 1. Those must be factors because when I plug them in here, I have to get 0. I have to get 0. Now, what we don't have are our last 2 mystery factors. So we don't know what those last 2 factors are. We need to be able to find them. So this is kind of like if they told us that 210 that we were talking about before is 2 times 3, and what we want is to know what is that last thing that we have to multiply by to get 210. Well, you might be able to just kind of do trial and error and figure it out, but what you would probably do if you wanted to figure out what that last factor is you would divide. You would do 210 divided by 2 times 3, which is 210 divided by 6, and you would get 35. So you would get 35, and you can say, oh, okay, that's what that last value is. We can do the same thing with polynomials. So what we have here is we have this big P of x. What I'm going to do is I'm going to divide by these two factors. So I'm going to do x to the fourth minus x cubed minus 7x squared plus x plus 6. We know right now it's equal to x minus 3 times x plus 1, and I'm going to just leave this as one big question mark now, because if I can find that one big question mark, it should be a quadratic, because it's two things multiplied together. Those two big question marks, when I multiply them together, should give me a quadratic. And if I can find the quadratic, there are other methods we know how to use to find the zeros of a quadratic. So I want to find that question mark. Well, I'm going to do that by dividing. So if we divide both sides by x minus 3 times x plus 1, this side as well, x minus 3 times x plus 1, then they're going to cancel out over here. And if I do polynomial division on the left side here, then I should be able to find what that question mark is going to be. And there are two ways we can do that. There are two ways we can do that, because if you look at this, when I did this division here, I did 210. What I did was I multiplied the 2 and the 3 to get 6. So one option is to multiply these two factors together using a box. We'll do that on the next page. And then we can do polynomial long division. The other option is we could divide individually. We could do, okay, well, what's 210 divided by 2? Well, that's 105. And now I divide by 3, which is 35. Either way you do it, you get 35. And we should be able to get the same answer for our question mark here, no matter which way we do it. If we divide by one at a time, first one, then the other, or if we multiply them first and then divide all together. So the first option we're going to do is by multiplying them and then dividing. So let's see what happens when we multiply x minus 3 and x plus 1. So I have to make a box for that. X minus 3, x plus 1. So x times x is x squared. X times negative 3 is negative 3x. X times 1 is x. And then we have negative 3 in our last box here. So we add all that together. Looks like x squared minus 2x minus 3. So that's what this product is right here. So what I have right now is that P of x, I'm not going to write it out again, but it's x to the fourth minus x cubed minus 7x squared plus x plus 6 is equal to this x squared minus 2x minus 3 multiplied by our question mark. We don't know what that other factor is, but we want to find it. So we're going to divide both sides by this quadratic. So we're going to divide both sides by this quadratic. So we're going to do that with polynomial long division. So we have x squared minus 2x minus 3. And we want to know how many times does that go into our big polynomial. X to the fourth minus x cubed minus 7x squared plus x plus 6. So x squared into x to the fourth, that happens x squared times. Multiply x squared by x squared, we get x to the fourth. Times negative 2x is negative 2x cubed. X squared times negative 3 is negative 3x squared. Subtract that off. Now we're subtracting all of these terms. Negative signs get a little hairy here. So let's take a look. X fourths go away. Negative x cubed minus negative 2x cubed. So that's going to be negative 1 plus 2, which gives us a positive 1x cubed. Might have to watch that a few times to see how that came out. Negative x squared minus a negative 3x squared. So we're adding again because we're subtracting a negative. So that's going to give us negative 4x squared. And then the plus x and the plus 6 come along for the ride. And now x squared into x cubed, that's just plus x. X times x squared is x cubed minus 2x squared, because it's x times x. And then x times negative 3 is negative 3x. Subtract that whole thing. X cubes go away. Negative 4x squared minus a negative 2, that's adding 2, is going to give us negative 2x squared. X minus a negative 3x is x plus 3x, which is plus 4x. And then we have a plus 6 here. So we need a negative 2 here to get to negative 2x squared. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 2x is plus 4x. And negative 2 times negative 3 is positive 6. Thank goodness we get a remainder of 0, which makes sense, because we know these are factors, so they should divide evenly into our polynomial. So we have found our question mark using long division. I'm going to get cut off here, so if you'd like to see the end of this problem, also with synthetic, you're going to want to watch the next video. See you soon.